thank you. Thanks for the introduction, and also thank you for the award. I'm very thankful to the O'Donnell family, the O'Donnell Foundation, and the TAMEST Academy, and the awards committee for this prestigious honor. So today I'm going to give you, in the next 30 minutes, a little bit of introduction of our recent work in the area of metamaterials and what they are, and a couple of applications of what we've been working on in the recent times. So when I speak about metamaterials to an audience that not necessarily has heard the word before, I like to start with one of the most common objects that interferes and affects light propagation or electromagnetic waves. That is a lens. We're all familiar with it, and we know what it does. It takes a beam of light and focuses or defocuses it to a point. What's interesting is that if you compare the size of this lens with the typical wavelength, that is the distance over which light changes in space, the sizes are very different, right? The light has a wavelength of about 1 micron, 1 millionth of a meter, but the lens is much bigger than that. And if you want to do something a bit more complicated than just focusing, then you end up with a very complex, setup, right? What we have in our optics labs. The reason for this is that the common interaction of light with conventional materials is quite weak. So you need a lot of volume to get an important effect. And when you're after complex operations, you need a very bulky setup with there's many wavelengths large. The area of metamaterials tries to go beyond this limit. The word meta means beyond in Greek. And we would like to squeeze the light-matter interactions, enhance them at the nanoscale, and get stronger anomalous effects with light and electromagnetic waves, but on a very small scale. An example of a prehistory of metamaterial is this cup, is the Lycurgus cup that was built in ancient Rome and is now housed in London in the British Museum. It's a cup that has a quite unusual effect. It looks red when it's illuminated from the back, but it looks green when it's illuminated from the front. So it changes color as a function of where you illuminate it from. And we don't know exactly how the Romans came up with this idea so long ago, this material, but we now know how it works because we can use microscopy and look in the glass, and we will find these tiny nanoparticles that are in the order of 70 nanometers, so much smaller than the wavelength of light. They're made of a very particular material, a composite and an alloy of gold and silver. And we know that these materials, noble metals, have very strong interactions with light. The electrons collectively oscillate the surface of these particles and therefore can boost these light-matter interactions and make them very strong at the subwavelength scale. We also know that this optical effect is achieved thanks to the specific choice of dimension, of density, with which, and material properties with which these structures are embedded in glass. If the Romans had chosen a different density or a different size of these particles, this wouldn't work, and the glass would become opaque or transparent or not give this optical phenomenon. Fortunately, today we understand much better how these things work, and we also can make materials much more complicated, as we have seen throughout the days today. And we can build materials like this that are made of nanoparticles that are arranged in specific, with specific orientations, alignment, density, shapes, controlling them with really nanoscale precision. And that allows us to get a lot of interesting effects and create devices and materials that are, have functional properties over much smaller scales, can be integrated on a nanophotonic platform, and give us a lot of interesting possibilities in very sub-wavelength scales. And that's really the idea of metamaterials. So what can we do with these materials? One of the most common phenomena that has been explored in this area is the phenomenon of refraction. This is, of course, a very classical problem. The refraction means that if I shine light on a given material, the beam of light changes its propagation direction and can be understood as a collective excitation of the molecules of the material that interact with the light, get polarized, and create this, as a collective response, this change of direction of light. As a macroscopic effect, this means that if you look at a straw on a glass of water, it looks broken because of this refraction effect. What metamaterials can do is to change the way in which refraction works. Typically, refraction always happens with positive angles that are closer to the normal if I go from a less dense material like air to a more dense material like water. But with metamaterials, we can build materials that have, for instance, a negative index of refraction. That means that light now, instead of bending towards positive angles, can bend the other way. And on a macroscopic scale, that would mean that the straw would look like this. This is actually just Photoshop, but it just gives you the idea of how it works. The reason it's Photoshop is that there is no negative index material in optics for visible wavelengths that in liquid form like this. But there are negative index materials that have been built for radio frequencies, for acoustic waves, for optical frequencies in solid form, and that really achieve this functionality of bending light the wrong way. And this was one example of what metamaterials can do and how they can interact anomalously with waves. In fact, recently we have been interested in exploring if metamaterials can be used not only to shape in an unusual way the wavefront of light, but also shape its spectral components. An example of this work that we have done in collaboration with the University of Pennsylvania, Professor Andrea, and the University of Benevento in Italy, Professor Galdi, has been the idea that you can nanostructure a material such that when you send an arbitrary spatial wavefront, as it emerges from the material, and this can happen over scales smaller or comparable to the wavelength, will calculate for you a certain operation of choice. So independent of the spatial wavefront you send in, you can calculate the derivative or the integral of that wavefront in the spatial domain. And that's quite interesting. This is an example, for instance, for the skyline of Westin that is imprinted on the input front of this metamaterial, and at the output front you get the second derivative of that image. You can get essentially edge sharpening in an analog fashion as light emerges from the structure. And you can take this idea a step further and take this element and put it in a feedback loop such that this structure has an eigenstate, a resonant state, this cavity that is a solution of a differential or an integral equation. So you can really calculate, actually, in an analog fashion, certain solution to an equation, mathematical equation. In this area, we have been looking for a while now, more than 10 years, the idea of making objects transparent or invisible to the incoming wavefront. And the basic idea is quite simple. If I have an object and I illuminate it with a certain electromagnetic wave, I actually hit its surface, and since the surface is mismatched with the free space, a portion of this energy actually gets scattered by the surface. And the idea is, can I engineer a metamaterial cover around the object that actually scatters a different type of light with an opposite sign, such that by interference at each angle, the scattering is cancelled. And if there is no energy scattered around because of destructive interference, then the object becomes transparent and light just has to go through the object. This is indeed possible with metamaterials. And in fact, over the years, we've worked metamaterials mostly for radio wave frequencies, so lower frequencies, longer wavelengths than light, that allow you indeed to scatter this negative phase light. We call it scattering cancellation. This, for instance, is an example of a material that is made of these metallic implants embedded in a high-permittivity ceramic shell. And the effective response of this material provides you this negative electric permittivity that gives you the desired properties. And indeed, if you measure the scattering from this object anywhere around the object, even in the near field, you will find the drastic reduction of scattering at the design frequency and over moderately broad bandwidth. how this works, if you look at the near field of the structure, this is an object that is illuminated by a radio wave. And as you see, the object, the energy is scattered around. You have shadow on the back of the object. But when you cover it with your metamaterial, then light goes through. And it's quite interesting how the energy just goes through the object, despite the fact that we are covering it with something that actually scatters, right? These are metallic structures and high permittivity ceramic. On their own, actually, they scatter. But the destructive interference of the cover and the shell allows you to get this effect in a robust way. We've used this technique to realize radio-transparent sensors or antennas, structures that essentially can receive and transmit information but do not scatter. So if you have a wave that comes from the outside, it just goes through these structures. And this is quite important when you have a lot of antennas placed nearby each other, because as I showed you, this effect works in the very near field. So you can have compact communication systems with a lot of antennas that do not interfere or affect each other. Or you can build an array of antennas that is transparent to a second array underneath it and allows radiation at different frequencies or for complex communication systems. Another, in this same thrust, one aspect we've recently explored has been the introduction of gain into the picture, of structures that actually are active. And this actually allows relaxing some of the constraints on bandwidth that these effects have if they rely only on passive materials, as I showed you before. The most basic example is this system that we recently built for sound, for acoustic waves. It's a sensor that is a loudspeaker, essentially, that is loaded with a resistive circuit that allows to pick up a portion of the signal. This is a conventional acoustic sensor, essentially. The idea is that when you pick up this energy, you are bound to actually scatter a portion of this energy and also create shadow on the back. What we did is to pair it with a material that is essentially a time-reversed image of the initial material. And we proved that under certain conditions, when you pair the two, you can actually allow, by the interference and the interaction of the two through scattering, create a system that allows to absorb the impinging signal, but at the same time provides zero scattering. And this is the experiment in which we showed that you can build essentially an invisible acoustic sensor based on this proper pairing of absorbing and gainy elements. And if you take this and wrap it around an object, then you can build what is called the parity time symmetric cloak, an active cloak that when it's illuminated by an arbitrary signal within a certain frequency range of interest, over time it will reach a stability, a steady state response that makes it completely cloaked, reproducing the impinging signal on the back and avoiding any reflections or scattering around the object. As another application of interest of these materials, we have been looking at ways to break one of the fundamental symmetries with which waves like light, sound, or radio waves travel in space. This is called the Lorentz reciprocity or time reversal symmetry. The idea is that if I am a source somewhere in space and I emit a signal and I have a receiver somewhere else, the transmission through an arbitrary material or an arbitrary volume is reciprocal, is symmetric. It means that if I can talk to you, typically you can talk back to me. There is a symmetric channel of propagation. In mathematical terms, this is written here. It's known in electromagnetics as Lorentz reciprocity theorem. And it applies to a very broad range of materials and systems, and has a lot of implications in many communication, energy harvesting systems, and I will discuss them in a moment. It is interesting in many cases to break this symmetry of transmission. The most typical example is the case of an isolator. An isolator is a device that allows me to transmit but not having to listen to the echoes, the reflections from the observer, and obviously this is very important for protection of sources, but also for to eliminate interference and noise from complex systems. The generalization of that is what is called the circulator. That is a circuit device that allows you to transmit the signal from port 1 to port 2, but when the signal comes back from 2, gets into 3, and it's completely isolated from 1. Why is this 3-port system so important or known in the circuit community? Because it enables what is called the full duplex communications. It allows you to place an antenna here and transmit a stream of data, but at the same time, the same antenna on the same frequency channel can receive a stream of data and route it to a receiver. What's important to get this effect right is that there is a strong isolation, because typically we transmit much larger power than what we receive. So it's important there is no leakage of this stream, this signal, into the receiver, such that we can just receive what is coming back. Interestingly, this is possible to achieve. So today we can break reciprocity using components like this. They are on the market. You can buy them online. But what you notice is that, again, these systems are quite bulky, are quite heavy, and also costly, because they are all based on magnetic materials, on ferromagnets or rare earth materials that have the property that when you apply a magnetic bias, they allow to break reciprocity, because this bias is odd under time reversal symmetry. It does not change when you change the direction of propagation, and that breaks the symmetry. There are a lot of reasons to get rid of these magnets. Of course, they are not easily integrated on silicon, so you cannot have a circulator on your cell phone. Today, we cannot use these important devices in cell phone applications for this reason. The materials are costly, so these devices end up being quite expensive also for those applications for which they are used, like in radar applications or RFID. And they come from regions of the world that not necessarily are friendly or may be friendly in the future. So one of the ideas we have been looking at is if we can use metamaterials to replace these magnets. And to do that, we got inspired of how these systems work. If you look at the ferromagnetic molecule at the microscopic level and you apply a magnetic bias to it, what you find is that the degenerate states, energy levels of this molecule get split when you apply a magnetic bias. So there is a preferred sense of spin for the electrons when there is a magnetic bias that happens at a lower energy level than the other one. This split is really what breaks time reversal symmetry, what breaks reciprocity. And if you use it in a smart way, if you engineer your device in a smart way, you can actually build a circulator out of these components. However, magneto-optics effects are small, and that's why you need big magnets to get a substantial effect. What we suggested is that you can mimic this response on a meta-molecule, on an artificial molecule that is composed in the simplest possible scenario of a circularly symmetric cavity that on its own has two degenerate modes. Essentially, this cavity can resonate for a wave spinning right-handed or left-handed at the same frequency, the same energy. However, if I start moving a medium inside this cavity, apply what is commonly called the angular momentum to this cavity, then the resonance frequency is actually split in a way that mathematically is very much analogous to what happens to a magnetically biased molecule. So the resonance frequencies for the mode that spins against the spin of material in the cavity has a lower frequency than the one that spins the other way. So this is an effective Zeeman splitting that happens in the cavity without the need of magnets, but because of an angular momentum bias that breaks time reversal symmetry. Based on this effect, we envisioned a circulator for sound. There are no circulator for acoustic waves on the market because magnetoacoustic effects are even weaker than magneto-optic effects. So we started with sound, and we found that indeed if you take a resonant acoustic cavity and you plug 3 waveguides to it, you feed it without doing anything else, at resonance power splits evenly between the 2 channels for symmetry as expected. But if now I start spinning the material inside, air in this case, you see that now sound from port 1 goes into 2 and 3 is completely isolated. The standing wave that you excite in the cavity actually gets rotated. You see it's excited asymmetrically, and that's because of the interference between the 2 spinning waves. And then when you excite from 2, actually the wave goes to 3, and from 3 to 1. So interestingly, this works like a circulator for sound. What's quite interesting is that the speed with which you need to spin air in the cavity to break this phenomenon is very small compared to the velocity of sound. It's 500 times smaller. And that's because our resonant cavity enhances sound-matter interactions. That's exactly what I discussed at the beginning of this talk. Based on this, you can build your own circulator. It's actually quite simple. It's 3 CPU fans that you can buy online, put them inside a circular cavity, then you plug 3 waveguides, and you can actually listen with your own ear that when the fans are rotated at the right speed, the sound goes from port 1 to 2, but doesn't leak to 3. And we were able to measure in this device up to 40 dB of isolation. This very rudimentary proof of concept of the idea. We also extended this idea to electromagnetic waves. They go much faster than sound, so you cannot really spin your cavity mechanically like what we did for sound, but you can spin it electronically. You can build 3 resonators and modulate them in time such that the circuit looks like it's spinning for an impinging signal. And again, the modulation can be much weaker than or much slower than the signal itself for the same reasons. And based on this, we built this RF circuit that essentially realizes a circulator printed on a circuit board without need of magnetic effects. It's just based on components that you can find in a cell phone or in any electronic component. So you can build your circulator on chip. It's also tunable in real time, and this idea was licensed recently to Silicon Audio, and we are commercializing the idea because it can have quite an impact on cellular or also radar systems or RFID devices. You can do the same trick with light. In fact, this is a nanophotonic circulator. Nanophotonics is kind of the next big thing in communications because we are trying to do more and more with light rather than radio waves. Of course, they offer much larger data rates because the frequencies are much larger. But one of the components that is missing in a nanophotonic system is an isolator or a circulator, and it's a very important component for many applications. With this idea, you can now envision these nanophotonic isolators on chip that require nothing but what already is on a silicon photonic board. Another important implication is of reciprocity is the limitations of energy harvesting devices. If you have a solar panel or a thermophotovoltaic device, reciprocity forces it to absorb. If it's a good absorber, it will be also a good emitter at the same frequency in the same direction. So you lose some part of the impinging energy, or the one that you absorb, by re-emission towards the source that is wasted. And for antennas, same problem. If I have a very good antenna to transmit, I'm prone to listen noise and echoes from the same direction. With systems like this, you can actually break these fundamental constraints. So you can improve efficiencies in energy harvesting and in communication devices. And in fact, in this area, quite recently, this is a paper just accepted in PNAS, we showed that you can impart a linear momentum to an impinging, to an antenna. This is actually how it looks in the lab. It's a compact antenna that whose elements are modulated in time in a linear fashion such that when a signal goes and comes back, sees 2 different antennas. So you can engineer the structure such that it is a very good emitter, but it doesn't receive back from the same direction or even from any direction, as you see in this plot here. Finally, the last idea in this same context is the one of now going back to a material. I started showing you what metamaterials are. Now we have a building block that is very efficient at creating this very unusual propagation, this one-way transmission. Can we build a material out of that? And something interesting happens when you consider an hexagonal lattice of these elements that individually break reciprocity. If you track how the signal would flow in this structure, it would flow only on the edge of the structure. It would have this type of propagation and over a finite bandwidth, not just for a single frequency. This is quite interesting because it's the analog for electromagnetic or acoustic signals of what happens to electrons in topological insulators. So this is a topic of great interest in condensed matter physics, for which these topological insulators have topological properties of the energy band diagram that allows to route electrons one way only on the edge of the material. And essentially, this metamaterial made of these non-reciprocal elements can actually build efficiently a one-way edge waveguide, very reconfigurable, that depends just on the edge structure of the material, that can route signals over broad bandwidths in the structure, but not in the bulk, not in the center of the array. Based on this, we proposed this topological insulator for sound that allows you to route sound on the edge, whatever happens to the edge, never comes back into the bulk, and never is reflected back, whatever happens to the edge. And you can build these robust, reconfigurable waveguides that route around the domain wall of this metamaterial. And that essentially concludes my talk. I showed you that Metamaterials is a very fertile platform to change the way in which we are used to tailor propagation using materials. They can provide very strong wave-matter interactions and can allow you to build compact devices at the subwavelength scale that interact with light, with sound, and with radio waves in very unusual properties. As I showed you, you can build one-way structures, cloaks, electromagnetic transparent objects, and much more. Thanks very much for your attention. Yeah.
You're making these elements much smaller than the wavelengths of the energy that you're dealing with. To what extent does the performance of these depend on the precision of those elements that are already much smaller than the wavelengths across the
Yeah, that's a very good question. So, of course, this depends a lot on the application you are after, right? The typical disorder that you may have in these nanostructured materials will affect strongly the performance if the structure is very resonant, if you have a resonant effect. But for instance, what I just showed you in the last couple of slides, these topological metamaterials, as we define them, that are based on these lattices of very unusual molecules, by definition are very robust to disorder or changes because of the way they are built. So actually they're called topological because these properties are based on the topology of the band diagram, and therefore they are very robust to continuous changes in the band diagram that can be caused by disorder. So I showed you, for instance, this disorder on the edge that would still allow to get this broadband propagation or signal transport throughout the structure. So there are ways to address these issues. But if you are after very resonant phenomena, then there will be issues caused by disorder or noise.
Maybe I didn't quite get it, but you had a cloak for electromagnetic waves, and you had a cloak for acoustic or pressure waves. And it looked like the electromagnetic wave went through the cloak and the object. But the acoustic one went around.
Yes,
Can you
that's
elaborate?
correct. Yeah, very good question. This, because there were two different objects. So if the object is actually is not absorbing or is not conducting, so it allows propagation in the material, but it scatters only because of impedance mismatch, as it happens in many cases, then the cloak chooses to let the wave go through the object because it allows actually to relax some of the constraints. But if the object, like in the case of an antenna, is actually a metallic object or something that does not allow propagation inside, then the cloak is actually forced to route the energy in the volume of the cloak. So it will actually flow on the surface of the object and go back to cancel the shadow. In that case, you will see that the effect is the same. But the fact that the signal has to route in such a smaller volume has some implications in the bandwidth you can achieve or the the breadth of the response, basically. Thank you.